Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. In today's lecture, we will discuss the optical property of semiconductor materials. We will try to link the optical property with the band structure of semiconductor material, how these two properties are linked with each other, and modification in the band gap can result in a change in the optical property of semiconductor material. This topic is the part of the course outlines of nanophysics and technology. Actually, we have the optical property starts when lights or photons interact with matter. So depending on the energy of that photon, the electron could be absorbed, it could be the photon could be absorbed, it could be transmitted, or it could be scattered in different directions. So actually the energy of that photon is given by E is equal to h now, or we can write the same equation as E is equal to hc divided by lambda. Now here is the frequency of the radiation, or the frequency of that photon which is coming, and h is a Planck constant, and its value is 6.62 multiplied by 10 to the power minus 34 joule second, and we have c, that is actually the speed of light in vacuum, and its value is 3 multiplied by 10 to the power 8 meter per second, and here lambda is the wavelength of radiation and E is the energy of that particular photon. So how the refraction occur, and how the electron interact with that matters. So the transmission or refraction light dissort electron cloud. So there is no transmitted light in the first case, and in the second case we have transmitted light, and the electron clouds is distorts. So the velocity of light in a material is lower than this value in a vacuum, and that is actually the ratio between for a particular material, for a particular medium, or for a particular material, and that is called as index of refraction. That is actually the ratio between the velocity of that light in vacuum to the ratio to the value of velocity of that light in that particular medium. So we have different value of n for different materials. So here we can see how the light bends when it passes through a transparent prisms. So we have the different values of n for different materials. Ranges from for typical glasses it is around 1.5 to 1.7. For plastic it is around 1.3 to 1.4. Is actually the ratio between the velocity of light in vacuum to the velocity of light in medium, in that particular medium. So similarly in diamond we have high index of refractions, or refractive index. So total internal refraction also occur in some cases. We did not discuss the absorption in this case, because absorption was already discussed in the we did not discuss the absorption was actually discussed in the last lecture, where we discussed the band structure. I mean when a photon whose energy was equal to the band gap energy, so that photon was absorbed, and that absorption will occur by moving an electron from the valence band toward the conduction band. So as the electron cannot remain for longer time in the conduction band, so when the electron hole pair meet with each other, so that leads to the creation of another photon. So we did not discuss the ideas of photon absorption in that particular in this lecture, but anyhow we will discuss the refraction and that particular area. So we have total internal refraction where n2 is less than n1. So what happened, there is some thing that occurs. We have two angle of incident and angle of reflection, and that is actually the ratio between if we see that n2 is less than n1, so n1 divided by n2 will be equal to sine alpha 2 divided by sine alpha 1, and fc is actually the critical angle here. So fc, if the fc exists when f2 is equal to 90 degrees, so what happens, this is called as a total internal reflection. For f1 is greater than fc, what happens, the light is internally reflected, and this is called as a total internal reflections. So in this case, what happened, we have fiber optics cables that are the examples of the total internal reflection, and it is created in low N material so that the light will experience total internal reflection and not escape from the optical fiber. So this is widely used in very wide range of applications for the transmission of data from one place to another place. So example, some of the example are the diamond in ear. When if we have the what is the critical angle alpha for light passing from diamond, it's refractive index N1 is equal to 2.4 into air is refractive index is equal to 1. So what happened? So we have in this case lambda 1 is equal to 5 1 is equal to 5c and 5 2 is equal to 90 degrees. What happened? After the calculation, we can see that the critical angle in this case is equal to 2.24.5 degrees. So this is some information we get that the critical angle between these two particular medium is equal to 24.5 degree. So this is so when light interact with solid, so there are 4 different possibilities. So it depends upon the energy of that light and the photon. So normally it could be expressed in the form of equation, and that is the incident light is equal to, it might be transmitted, it might be absorbed, it might be reflected, it might be scattered in different directions. So there are 4 different possibilities for it. So this is actually the optical classification of materials. So we have some material that are transparent, single crystal, we have some material that are translucent, and we have some polycrystalline dense material, and we have some opaque material. So we have some polycrystalline porous material for that particular. So this is actually the optical classification of materials are based on that their optical properties. So the first thing what we need to discuss is the absorption. And absorption is very simple, as we discussed in the previous lecture. When a photon is coming and its photon energy is equal to the band gap energy of that particular material, so the absorption will occur, and the electron as a result of this absorption will move from the valence band toward the conduction band. So if an incident light having the energy that is equal to h nav, that is absorbed, so what happen? The electron will move from the filled state toward the empty state. That is, actually empty states are often located at the conduction band, and it will move through a band gap depending on the material, what type of material we are dealing with. But anyhow, the absorption will leads to the motion of electron, to the movement of electron from the filled state toward the toward the empty states. So unfilled electron states are adjacent to filled states. So near surface electron absorb visible light. So light absorption would happen, and how we can categorize it. So the amount of light absorbed by a material is calculated using Beer law, and that is equal to IT is equal to I naught e to power minus b beta L, where beta is the absorption coefficient of that particular material, L is the sample thickness that is mentioned in centimeters, I naught is the incident light intensity, and IT is the transmitted light intensity. So rearranging the above equation, we can have this new form, that is natural log IT divided by I naught dash, that is equal to minus beta L. So we have another property of the material, that is actually the reflection of light for metals. In case of metal, how the reflection occurs. So electron transition from an excited state produce a photon, and that photon is a type of reflection processes. So what happens? The electron from the conducting state, it moves toward the electron transition toward the lower energy levels. So photon is emitted from the metal surface, and this is actually called as the reflection process. So we have reflection of light from metal again that is mentioned as reflectivity is actually the ratio between IR to I naught, and its value lies between 0.9090 to 0.95. For metal surfaces it looks shiny, and most of the absorbed light is reflected at the same wavelength. Small fraction of light may be absorbed, and color of reflected light depends on the wavelength distribution, just like for case of metal, coppers and gold absorb light in blue and green, and the reflected light has gold color. And that is the reflection is mentioned in the term that is called as reflectivity. So for normal incident light passing into a solid having an index of refraction n is equal to reflectivity is equal to n minus 1 divided by n plus 1 whole square. So just like for the case of diamond, the index of refraction or the refractive index is equal to 2.4. So we can calculate the reflectivity from this equation, and that is 17% of light will be reflected. So scattering of light is also an important phenomena, that is actually the optical property. But in case of polymer, how the scattering occurs? So for highly amorphous and poor free polymer, what happen? There is very little or no scattering, or these materials are transparent in nature. So if we consider semi-crystalline polymer, so what happen? There are different indices of refraction of amorphous and crystalline regions. So the scattering of light at boundaries occurs, and there are highly crystalline polymers may be opaque. If we have highly crystalline polymers, so it may be opaque. So just like in case of polystyrene, that is amorphous, it is clear and transparent, and you have low density polyethylene, milk cotton, so it is opaque. So how the selected light absorption in semiconductors occur? So it is the absorption of light frequency nav by the electron transition if H nav is greater than E gap. So what happened? The electron move from the valence band toward the conduction band, from the filled state toward the unfilled state. This is in case of semiconductor, but the previous absorption was in case of metals. So there is a band gap, that is actually the gap between the top of the valence band and the bottom of the conduction band. So if we have photon, that is a blue light, and its wavelength is whose energy is equal to 3.1 electron volt, so it will be absorbed as a result of the if the energy or the band gap of that particular material is 3.1 electron volt. Similarly for the case of red, it will be only absorbed if the energy of that band gap in that particular semiconductor is equal to 1.8 electron volt. So it means this is actually the absorption and process in semiconductor material that depends upon the band gap of that semiconductor material. So that is why semiconductors are very interesting in the sense that it can absorb a wide range of light, and we can modify the band gap leading to the absorption of various wavelength photons. So we have the computation for the wavelength in this case. So that is the called as the minimum wavelength that could be absorbed, and that depends upon the band gap. Just like in case of germanium, we have Hc divided by Eg. The same equation is modified. In that case, we have Eg is equal to Hc divided by lambda. But for cross multiplication, we have lambda is equal to Hc divided by Eg. The same thing, only just put the value. So we can get the minimum, that is called as threshold wavelength for germanium, and its value is equal to 1.86 micrometer. So similarly for silicon, the same value could be obtained very easily. We can follow the same equation over here, and its value is the minimum threshold value is 1.13 micrometer. So there is the presence of donor or acceptor level state for light absorption and other wavelengths. If we add the donor or acceptor level in a semiconductor material, definitely the optical property or the absorption property will be changed. So we have color of non-metal, that is due to the color determined by the distribution of wavelength. It might be transmitted light or re-emitted light from the electron transition. just like in case of cadmium sulfide CDS, whose band gap is equal to 2.4 electron volt. So what happens, it absorbs light higher than visible light, especially the blue and violet, and light result from red, orange and yellow light that is transmitted. So similarly, another example is Robbie's, that is actually alumina L203 plus 0.5 to 2% atomic percent of Cr2O3, and that is actually transparent and colorless when its energy is greater than when energy is 3.1 electron volt. So it has also very interesting colors that is mentioned here. So luminescence is one of the optical property, and what happen in luminescence, that is actually the re-emission of the light by a material. So material absorb light at one frequency and re-emits it in another frequency. This is called as a re-luminescence process. So it is trapped. The donor or acceptor states are introduced by the impurities or defect, and that plays a major role in creating the light of different wavelengths. So what happened is actually the valence band and conduction band. So in between the valence and conduction band, this region is called the band gap. So the most important states are the trap states, and these states are created or introduced due to the defects in that particular solid, or by adding impurities in that solid. It introduces some isolated state in the band gap, so that changes the wavelength of upcoming light. So if the residence time is trapped state is relatively long, that is greater than 10⁻⁸ seconds, is called as phosphorescence. But if we have short residence time for that is less than 10⁻⁸ seconds, so it's called as fluorescence. So just like in toys that glows in the dark, and charged toys by exposing them into light. So re-emission of light over time, that is called as phosphorescence. So we have photoluminescence, and in case of photoluminescence, we have arc between the electrode that excites electron in mercury atom in the lamp to higher energy level. So what happen, as the electron falls back into their ground state, lower energy level, so what happen, ultraviolet light is emitted, and inside surface of the tube line with the material that absorb ultraviolet light and re-emits visible light. So this is actually indirect process for the creations of photon, and one of the important optical property of the material, that is we can adjust its color by doping with metals, cations, especially sp3 or Mn plus 2. We have cathodoluminescence, and in case of cathodoluminescence, we use it is often used in cathode rays tubes device, that is especially in TVs and computer monitors, and inside of the tube is coated with a phosphorus material, and this phosphor material bombarded with electrons. So electron in phosphorus atoms excite to higher energy states. So what happen, photon or visible light emitted as electron drop back into ground state when it come from higher energy level to lower energy levels. So what happened, visible light photon are emitted. So color of emitted light, that is photon wavelength, depends upon the composition of phosphorus, and we have different phosphor for that, just like Z and S we have blue color, for Z and CD and S we have green color, and for Y2O2S plus 3% EU we have red color. So laser is also one of the interesting optical property of the material, that is actually the light amplification by stimulated emission of radiation. We have also discussed this in earlier classes, but in today's lecture we will also put a brief survey on the laser, or a very short discussion on the laser. So the laser generate light waves that are in phase, that are coherent, and that travel parallel to one another. So its operation, laser is widely used, and it has very interesting applications. So what happen in laser, the most important thing what we need is the population inversion, and more electrons need to be in excited state than in ground state. This process called as a population inversion. The electrons are excited from the valence band toward the conduction band. So if you populate the excited regions or excited excited states of that material. So this is called as population version, and there is some spontaneous decay of this photons of this electron toward the ground states. So this spontaneous decay leads to the spontaneous and stimulated emissions of photon, and that is actually the laser photons. This diagram briefly show how the laser photon are created. The electron are shifted from the valence band toward the conduction band. We have non-radiative transition of the electron from this state toward this metal stable state, and finally at the metal stable state we have stimulated emission, and that stimulated emission leads to the creation of laser photons. So it's often used, laser are often used in different type of application. Just like in this case, we have use the laser electron enlarging material to the excited state by flash lamp. Some other stimulated emission. This is a simple phenomena where we can have a stimulated emissions. That means how the electrons are moved from the ground state toward the excited states, and that leads to the stimulated emission. And as a result, the electrons are forced, or it is stimulated to move toward the ground state, leading to the creations of laser photons. So we have continuous wave levels. Different type of lasers are used, and that depends upon the application and even the energy of that particular laser. So lasers are such particular wave lasers are used in welding, drilling, but that are the high energy lasers. So we have semiconductor laser application. It is used in different type of applications, just like applying strong forward bias across the semiconductor layers. We have this is used in this material. So that also leads to the creation of laser electron hole pairs generated by electrons that are excited across the band gap. So what happened? The recombination of electron hole pairs generate the laser photon. So this is also the laser process. So we have wide range of application of laser, just like in CD player and high resolution DVD players and fiber optics, and so other applications are in optical phenomena. Lasers are light emitting diode is used. So we have interesting applications of laser over here where it is widely used. So this is something about the optical property and discussion of the optical property and how it is related with the band structure of the material. I hope we will have some relevant lectures in the upcoming lecture, inshallah. Thank you very much.